Howdy! This is your friendly neighborhood physics teacher. I am friendly, I promise. And I am going to go over the review for your test. That's Wednesday or Thursday. Tomorrow or Thursday. So, I'm going over the review. I promised y'all I would throw in some frame of reference questions. I realized those didn't make it on the review. So at the beginning, I'm going to do some frame of reference questions. And then I'll jump into the review. This is Unit 2. This is 1D motion. Just a reminder, there is a Quizlet on Schoology that you can go over. No, there won't be exactly questions like, what is acceleration? Or anything like that on the quiz. But knowing your vocabulary words will help you a lot on the quiz. Make sure you can convert. There is a converting question on here. So make sure you remember to convert. I know that's Unit 1. But physics builds on top of each other. It does not go away. It'll come back to haunt you. So, know how to read a position versus time graph and a velocity versus time graph. If you're still having trouble with that and this review doesn't help you, I did make a specific graphing review video that's already posted on Schoology. So please check that out. Same thing, be able to determine if something's going positive or negative by context clues. Be able to use all formulas, the correct units with each variable, and understand frame of reference. So let's go with the understand frame of reference. So disclaimer, these questions are not on your review. These questions I'm adding to the video so we can make sure you go over, we can touch base on what frame of reference is, by doing some practice problems. So, it says in figure 1 below, which the figure did not come, so I'm going to have to draw it. So you get my lovely figure 1. Below, 2 trains are speeding past a train station with people waiting on the platform. Okay, so let's make our little train station. So, you know, we don't want it, just in case it rains, you want to give their nice little station something to, so they can hide underneath, and there'd be something right there. So there's people underneath there. So people I mentioned that there's trains. So there's 2 trains. So we have a train 1. We're going to do a train here. And my trains are going to be very boxy because that's how I roll. So train 1, jump, jump. And train 2. Joop, joop. Here, we'll give it a little smokestack so we know it's a train. Okay. So now, both trains are traveling at 75 miles per hour. There's a plane flying overhead. So let's work on our plane. Plane flying overhead. Little propeller. Go back to the little propeller. Wing. Wing. There we go. Got a plane going on there. We need to add so we said that the train is moving at 75 miles per hour, 75 miles per hour. The plane is flying overhead at 300 miles per hour. And there's 2 cars leaving the station. And so 2 cars leaving the station. Our cars are going to be light blue. So 2 cars leaving the station. And they're leaving at different velocities. The first car is traveling at 30 miles per hour. The second car is traveling at 45 miles per hour. So all the moving objects are moving towards the positive direction. So we're just going to say a positive direction would be in that direction. So that direction is going to be positive because it's to the right, sort of, but to the right. So Answer questions below in a separate piece of paper. Well, we're answering the questions on here. Excuse me. At what speed and direction is the platform moving if the frame of reference is? So we're dealing with the purple. Our platform's purple. So now, if you think about frame of reference. So our frame of reference is the Earth. What we mean by Earth, we don't have a light green. So it's the fact that earthbound. We have Earth. So when we're standing there, we don't feel the Earth moving. Yes, the Earth is technically moving, but in our frame of reference, what we call Earth frame of reference, the Earth is not moving. So, since we're doing the platform, we'll make it purple. And so the platform compared to the Earth is what? Not moving. It's not moving. But compared to train 1, which I did not label the trains. I'm sorry. We'll say train 1 and train 2. So compared to train 1, the platform is moving 75 miles in the negative direction. Miles per hour in the negative direction. Just make that negative 75 miles. And then according to the people aren't moving. So therefore the platform's not moving. So again, it's not moving. So you have to think about what from a reference you're dealing with. So, oh no, our pictures are going to go away I'll scroll back and forth. Okay, so at what speed the direction is train 1 moving in the different frame of reference? So dealing with train 1 to train 2, if we notice they're moving at the same speed. So if you're in train 1 and you looked over and saw train 2, you weren't able to see any of the ground moving, would it seem like the train was moving? Hopefully you said no, because they're moving at the same speed. Since they're moving at the same speed, they would look like they're not moving. So we're going to switch this to red, since they are in red. So it'd look like it's not moving. Okay, the second car. So the second car, again, I forgot the label. So car 1, car 2. So the second car is moving at 45 miles per hour in the same direction as the train. So since they're moving in the same direction, you have to figure out what the difference is. So the train's moving at 75, the car is moving at 45, so you would have to subtract your number. So 75 miles per hour minus 45 miles per hour equals, dun 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 dun, see if you can do math in your head, yay, get 30 miles per hour. So it seems like the train is going only 30 miles per hour compared to that car. Which, think about it, and if you're driving anywhere in Texas that's kind of rural and there's a train, you end up driving next to a train. Yeah, the train might be going 90, but if you're going 70, it only looks like the train's going 20. Because you have that frame of reference. You're already moving, the train's moving, just according how much faster the train's moving compared to you. So the train's only moving 30 miles per hour faster than the car. So it only seems like the train is moving at 30 miles per hour. And to the Earth, well, again, the Earth's not moving, so it just seemed like it's moving at 75 miles per hour. Again, in the positive direction. All this because they're all moving in the positive direction. Be positive. To the plane, now, we're all moving in the positive direction, but again, we have to subtract. We have to take the moving into consideration. So the plane is 300 miles per hour minus the train, which is 75 miles per hour. They're both moving in the positive direction. It just seems like the train is moving a whole lot slower than what it really is. Or not a whole lot slower. Stop. I flipped it. See, teachers make mistakes too. It's good for you to see that. Teachers make mistakes too. Okay, to the plane. I was about to show you how fast the plane looked like it was moving to the truck. What I was about to do, what I was setting up, I was about to show how fast the airplane looks like is moving compared to the train. But we're trying to figure out how fast the train looks like compared to the plane. So we have to do 75 miles per hour minus your 300 miles per hour. So it doesn't seem like it's moving really fast backwards. So it seemed like it's moving really, really fast backwards. So you kind of do some mental math. I'm going to do a little bit of mental math. Okay, so that'd be 5. And that'd be 2 miles per hour. So it seemed like it's going really, really fast the negative direction because think about it. The plane is moving really, really, really fast in the positive direction. It's going to leave the train in its wake. It's going to just be smoking. So it seemed like the train's moving so slow, it's almost moving backwards. So that's a common mistake. You just saw me make that mistake. You try to do one over the other. It's like, oh, I want a positive number. But you always put what you're comparing first. So we're trying to do what train 1. So train 1's got to first minus whatever the object we're comparing to. So what is the speed in the direction? What speed in the direction is the first car moving if the frame of reference is to the second car? So again, you can just start subtracting. So you end up doing the so it's first car to the second car. So you end up doing 30. So you end up doing 30 miles per hour minus your 45 miles per hour. It's going to seem like the car is moving backwards, going the negative direction, because you're going to end up passing the car. Since you're passing it, seems like it's moving backwards, and end up being at a 15 miles per hour. Train 2, again, you do the 30 minus what the train is, and you keep going that direction. So again, this one's going to seem like the car is moving a whole lot slower, and you end up getting 45 miles per hour. The people on the platform aren't moving, so it seems like the car is just going at 30 miles per hour. And to the Earth, again, the Earth's not moving, so it just seems like the Earth's moving at 30, is moving at 30 miles per hour. And to the airplane, again, it's going to seem like it's moving really fast backwards. So it'd be negative 270 miles per hour. So there is one more set of problems, and basically it's train 2. We go back to red. Train 2, train 1, train 2 are moving at the same rate, so it's like not moving. Airplane, so it'd be the exact same one. This will be just like be just like D. The first car, did I do this? No, I did the second car. I didn't do the first car. So the first car, your first car was 30 minus 75. Nope, let's have to flip it again. Looks like I'm doing something wrong. Let's flip it again, so it'd be 75 minus 30. The reason, again, you always put what you're dealing with the train, so the 75 has to go first. See, I almost did it again. It's a very common thing to mess up. You deal train, 75, that's got to go first. Minus your 30, so you get 45 miles per hour. And then the platform would just be 75 miles per hour. So hopefully that'll help you with your frame of reference. I know I got kind of redundant near the end, but I want to give you as many practice problems as I can. So now, to the review. So your X is position. For X is position. The units that go with position is meters. Delta means change. So your delta means change. Or change in. So basically change in position. Which means your displacement. Again, that'll be meters. I, that's a subscript I, V, so V's velocity, so the subscript is initial velocity. That's going to be meters per second. We get that by dealing with the slope of the, we get that from slope of the position versus time graph. F means final velocity, meters per second. Delta means change, so change in velocity, again, which is meters per second. Delta T, we have change in time, which is just in seconds. And then A is for acceleration, which is in meters. Meters per second squared, or meters per second squared. So I would know these. These would be very handy to know. You have your equations. Now, don't forget on your printout, I actually forgot to add the squared. So make sure you add the squared to your information, because I forgot to add that. So now, for question 1, drawing it out would help a lot. So I'm going to do some drawings. So I'm going to use your velocity versus time graph, and I'm going to do actually 5. I know there's only 4 things there. I'll have 4. I'll do the 5th one up here. One that doesn't relate up there. So, number 1. So, we have velocity. That velocity is telling you direction. It's telling you direction. Your acceleration is telling you to look at your slope. So this is your positive, that's your negative, positive, negative, positive, negative, positive, negative, Positive, negative. Again, that's dealing with your direction, positive or negative direction. It's according to what quadrant you're in. And your slope, if you have a positive slope or a negative slope. So we're in the upper quadrant because we're in the positive direction and a positive slope. So positive slope means you're sloping up. So now think about what's going to happen to your numbers. You go 0, 1, 2, 3. Your numbers are getting bigger as time increases. So as numbers get bigger as time increases, that means you're speeding up. So now let's look at the second one. So positive, so we're in the positive quadrant, but a negative slope. So you're sloping down. Again, look at your numbers. You would be like 3, 2, 1, 0. Your numbers are decreasing. So that means you're slowing down. For your third one, you're in the negative quadrant, but a positive slope. Positive slopes go up. But again, pay attention to your numbers. When you go down the 0 line, they kind of flip. So they start going 1, 2, 3. So in this case, you're going 3, 2, 1. Your numbers are getting smaller. So you are slowing down. Last one. So in this case, you have a negative, negative. So you're in the negative quadrant doing a negative slope. But remember your numbers, you go 1, 2, 3, so your numbers are getting bigger, so you are speeding up. Another thing you can look at is think about how you multiply positives and negatives. So a positive and a positive give you a positive. Multiply two positives, you get a positive, so it's speeding up. Multiply a positive and negative, you get a negative, so it's slowing down. Multiply a negative and a positive, you get a negative, so it's slowing down. Multiply a negative and negative, get a positive, so it's speeding up. Now, I had a couple of people ask me in class today, how in the world do you get constant speed? So that is going to be our fifth one, and it's when you have a straight horizontal line in your velocity graph. So that means it could be negative or positive, but your slope, your acceleration is 0. And that's how you would get a constant. So it could be negative or positive. But the key thing is you have to have a negative, or you have to have a 0 acceleration. So your slope has to be 0. So there you go. So now we're going to be drawing a position versus time, velocity versus time, and acceleration versus time graph. So we'll be doing position versus time, velocity versus time, and acceleration versus time. So a person walking north, so that's a positive direction, at a constant speed. So that means our slope is constant. So to have a constant slope, you have a diagonal line. And it's positive, so you're going up. Going up the position versus time graph. So you're positive, so you're going to be in this quadrant, but constant speed, you show constant speed with a horizontal line and constant. And then your acceleration would be 0 because your velocity is not changing. For a person standing still. So a person standing still, you can be placed anywhere. You can be placed here, you can be placed on 0, you can be placed anywhere, okay? Any spot as long as it's a horizontal line, but you just want one of them. So I'm going to go with that one. It doesn't matter where you place it as long as it's 0. Your slope is 0. So therefore your velocity is 0. And if your velocity is 0, your acceleration is 0. Okay, person walking south and then back home. Now this one, it was kind of open-ended. I promise on the test, it will not be open-ended. We'll know exactly what you would need to do. It says walk south and then back home. It doesn't say at what rate. It doesn't give you any information like that. So you could have different graphs. I had some people draw walked. As long as you stopped at the same spot, you're golden. I had some people, go down here. They walked. So they made sure they stopped. They thought home was 0. I had some people, I didn't have any people, but actually I did have some people do this one. You accelerated. Or you slowed down and then you sped up. And I didn't have anyone do this, but you can have this type of graph. Any of those would be correct. Then you just have to deal with the velocity. So if we're looking at the pink one, you are speeding up to slow down. So you are speeding up in the negative. You're slowing down in the positive. For the yellow, you are slowing down in the negative and speeding up in the positive. For the blue, you're staying constant in the negative and then staying constant in the positive. And then for the green, it's the exact same thing. Constant. So of course for your green and for your blue, your acceleration would be 0. Because you have a straight line in the velocity. Your velocity is constant, so you're not changing, so you have no acceleration. You are changing for the next two. For your pink one, you're accelerating. For the yellow one, you're accelerating. So, kind of give you an idea for that. For a position accelerating north, now again, this one is specific. So you have position versus time, velocity versus time, acceleration versus time. So, you have a person accelerating north. So we need to show that's positive acceleration. So you start out shallow and go steep, which should give you a positive acceleration, and positive velocity change, and positive acceleration. There we go. Whoop. So how do you find velocity from the position versus time graph? The big thing is slope. The reason, because you have your slope as your change in y over a change in x, and your y for your position, your y is x, which is position. Your time, or your x is time, and that equals your velocity. Another way to think about it, that's how you get your meters per second, because position is in meters, your time is in seconds, so you get meters per second. Woohoo! So what is happening with the graph below? Again, the graph didn't decide not to make, so I will make the graph very quickly. It's going to be an extremely rough graph. Extremely rough, so please be patient. So we go like that, and we go like that, it goes like that, it goes like that, and it goes like that, and that. Okay, something like that. So I don't have the picture in front of me, so I don't know times or anything, so I'll give you the gist of the breakdown, and you can tell me what's going on from there. So 1, so our velocity is 0, so we're not moving. 2, we're in the negative direction, and our numbers would be getting bigger, so we are speeding up in the negative. So 3, we are slowing down because our numbers would be getting smaller. Be slowing down in the negative because we're still in the negative quadrant. So right here, so make that 4. 4, we'd be turning around. Because now you're going in the other direction. 5, you'd be speeding up because our numbers are getting bigger in the positive. Number 6, your velocity would be constant. In the positive. For 7, we'll be slowing down in the positive. For 8, we'll be turning around. Eek. For number 9, would be speeding up in the negative because our numbers would be getting bigger. Number 10 would be slowing down in the negative. For 11, would be constant velocity. Velocity would be constant. In the negative. Last but not least, we'd have 12. And I would be slowing down in the negative. So I kind of give you a gist of what everything's happening. So we're not moving, we're speeding up, we are slowing down, turning around, speeding up, moving constant, slowing down, turning around, speeding up, slowing down, constant, slowing down. So, and how do you find displacement from velocity versus time graph? You do area under the curve. I'm going to do curve in quotations. The big reason why I'm doing curve in quotations is because if you look back at our graph, do you see any curves? Hopefully your answer is no. So you'll just be dealing with your area. So you have area of a triangle, which is 1/2 base times height, or you'd be doing area of a rectangle, which is base times height. And remember, if you're trying to find displacement, direction matters. So anything above is positive, anything below is negative. So then you would just add up the top, subtract the bottom, and you're good. So 7. Ben Russian Get it? Been rushing? Huh? Okay, it's fine. Is waiting at a stoplight. When the stoplight turns green, Ben accelerates from rest. That rest is a key word. That rest is telling you that your initial velocity is 0. And it's saying that you accelerate at a rate of 6 meters per second squared. So that's your acceleration for a time of 4.1 seconds. So that's telling you your time. And we're working for our displacement. So if we scroll up to our equations, so we need to find acceleration, or we need an equation that has acceleration, change in time, initial velocity, and change in position. Let's scroll up to our equations. So we're going to be focusing on the big four. So we're going to be focusing on these right here. So we can't use this one because it doesn't have we don't have final velocity. We don't have final velocity. Oh, displacement, initial, time, acceleration. Ooh, that looks like a good one. Can't use this one because it doesn't have final velocity. So it looks like we are using this one, which if you remember how they're numbered, it's technically your third equation. So we write down our third equation. So our third equation is your change in position equals initial velocity times delta t plus 1/2 a delta t squared. I get this question a lot. That squared only goes to the delta t. It's the only time that squared goes to the delta t. We plug in what we have. We're looking for our displacement. Our initial is 0. Our time is 4.1. 1/2. Our acceleration is 6. Our time again is 1.4, but don't forget about the squared. 0 times anything just goes to 0. So our delta x equals, you square your 4.1 and you get, sorry, I'm looking for my calculator. Give me 2 seconds. So 4.1 times 4.1, because that's the cool calculator I have. So 4.1 times 4.1 equals, it will give you 16.81. I knew it'd be 16. I just couldn't figure out the decimal. You halved your 6, so I'll give you 3. Like I said, that's just 0. So your delta x, you do 3 times that, and you get 50.43 meters because it's displacement. Can't forget about your units. No naked numbers running around. Okay? So that's that one. So for the next one, we're looking for his final velocity. So we can scroll up. So we have acceleration, we have time, and we have initial. So I think we can use the first one. Let's see. Yep, we can use this one. So we can use the final velocity equals the initial velocity plus a delta t. So we're looking for the final velocity. Our initial velocity was 0. Our acceleration was 6. And our time was 1.4. So we do 1.4, 6, gives you 24.6, and this is velocity, so meters per second. So you get meters per second. And that'll be that one. Woohoo! So let's keep going. We're almost done. 2 more problems. We got this. So if I move your desk 10 meters north, and I change my mind and move it 20 meters south, what's the distance and then what's the displacement? So I like drawing things out. So we have a desk. So I move it 10 meters north. And then I move it 20 meters south. Now remember, these are not position. Your displacement equation is final position minus initial position. But for distance, you just add them up. So it'd be 10 meters plus 20 meters, which gives you 30 meters. Don't worry about direction because distance is a scalar. It doesn't have direction. You have to deal with position. So your initial position would be 0. Your final would be at -10 because we're -10 off from where you started. So final is -10, initial is 0, so you get a -10 meters as your displacement. The negative just means south. So, or you can write it 10 meters south. That is technically correct. Awesome. So now, if you kick an empty can that is sitting on the floor and moves 150 centimeters, so that will be our displacement in 3 seconds, so that's our time. What is the acceleration? Your acceleration. It says it was sitting on the floor. So sitting on the floor, what does that tell us? Is it moving at the beginning? No. So our initial velocity is going to be 0. But now, in physics, remember we do the MKS system. So with the MKS system, it means we use meters, kilograms, and seconds. Is our distance in kilograms? No, it's not. So we got to do a little bit of converting. So 650 centimeters. We want to get into meters, so centimeters get shunned. We want meters, so for 1 meters, we get 100 centimeters. So to divide that by 100, you get 6.5 meters. So we'll use that as our displacement now. So we have initial, we have displacement, we have time, we're looking for acceleration. So if we scroll up, we look at our formulas. Scrolling. So we don't have final, so we can't use, we don't have final, so we can't use U. Don't have final. So again, we're with this one because it's the only one without final. So we're using the third equation again. I told you the third equation is the most active equation. So we're going to use our delta x equals v naught, not v naught, yeah, vt delta t plus 1/2 a delta t squared. So our delta t would be 6.5, our initial would be 0, our time is 3 plus 1/2. We're looking for the acceleration, our time is 3 squared. So, let's put this down a little bit so I have a little bit more room. So that just goes to 0, so we have 6.5 equals, and you 1/2 a, you square your 3, so 3 times 3 is 9. Now remember, when you're multiplying, you can move these around. So you can get 6.5 equals 9 divided by 2, because multiplying by 1/2 and dividing by 2 is the same thing. So you get 4.5a, we want a by itself, being multiplied, so the opposite of multiplying is dividing. So your acceleration will end up being 6.5 divided by 4.5, which will end up giving you 1.44. Don't forget your units, meters per second squared. There you go. So 10, if you drive your car 12 miles total during a 24-hour period and park in the same spot each night, why is your average velocity during the day 0 meters per second? Think displacement. Remember, velocity is a vector. So that all goes back to your equation. Remember, your velocity equals your displacement over time. Displacement is your final position minus your initial position. But if you park your car in the same spot each night, your final position equal each other. So is there a change if they equal? No. So no matter how long, even if it's 24 hours, if you have no change position, your velocity will still be 0. So that's a key thing, is knowing what displacement means. That's why going through those Quizlets will help. So hopefully this helps going through the review. I know it was a long video, but I wanted to make sure I went over everything kind of in detail. If you have any questions, please don't be hesitate to email and ask. I hope you have a wonderful night. Good night.